Hello, my name is Stefan Hermann and I'm presenting how wearables can be used to improve the quality of cardiopulmonary resuscitation, or short CPR. In our work, we compared 3 wearable carrying positions in their accuracy to estimate compression depth and rate. Let's start with some background on CPR. When performing CPR, chest compression quality is a key factor for cardiac arrest survival. However, providing high-quality chest compressions is very difficult. Current guidelines recommend that chest compressions should be provided at a rate of 100 to 120 compressions per minute and a depth of 50 to 60 millimeters. So far, many studies have shown real-time feedback of compression depth and rate lead to improved compression quality. Current technology focuses on special devices which are placed on a patient's chest. Those devices are very accurate but simply unavailable in most scenarios. Wearables, however, do not interfere with clinical workflows and are pervasive. Some wearable carrying positions have been investigated by previous work: handheld smartphones, smart rings, smartwatches, and Google Glasses. Previous work proposed different algorithms to estimate compression rate and depth. We compared 6 of them. Please find detailed descriptions in our paper. Studies from previous work collected mostly compression samples that were in the recommended depth and rate range only, but feedback is especially important when chest compression parameters are outside of the desired range. We performed a data collection study to evaluate 3 wearable positions: a wrist wearable, which can be seen on the left, a chest wearable in the lower right, and an eSense earable in the upper right. Both the chest and the earable location are evaluated for the first time. The participants performed chest compressions on a mannequin as shown in the center image. The mannequin's integrated displacement sensor provided gold standard measurements. We built custom wrist and chest wearables to integrate the same acceleration sensor that is used in the eSense earable. In this figure, you can see the custom-built wrist wearable, which resembles our chest wearable. It includes an ESP32 board and an MPU 6050. All 3 wearables sampled at a rate of 50 Hz. The data was transmitted via Bluetooth Low Energy to a smartphone, followed by manual synchronization with the gold standard measurements of the mannequin. Let's talk about our results. 20 people participated in our study, and more than 5,000 compressions have been recorded. The heat map shows the distribution of the collected compression depth and rate samples. The brighter the color in the image, the more compressions were recorded for the specific rate and depth. The target ranges, as recommended by current guidelines, are marked by the white dotted lines. While most studies from previous work focused on collecting samples in the target ranges only, the heat map shows that we collected a broad range of compression data, improving the reliability of our findings. This graph depicts the estimation accuracy. The black lines indicate the target range as recommended by current guidelines. The target range for compression depth is 50 to 60 millimeters. The overlaid error bars show the median depth estimation deviation. To put the estimation errors into perspective of our collected data, a baseline is provided. The baseline at 9.5 mm is the median absolute deviation of an educated guess. Depth estimates obtained by the earable positions had the highest error with an absolute median deviation of 5.9 mm. We also tried tensor fusion, yielding a slight improvement in accuracy. However, all positions outperform the baseline significantly and have an error of less than 10% compared to the recommended compression depth. The recommended target range for compression rate is 100 to 120 compressions per minute. The baseline was 18 compressions per minute. Rate was estimated with a median error of less than 1.6 compressions per minute at each wearable position, or less than 2% compared to the target rate. Limitations. First of all, the study was performed on flat and hard ground only. Flat and hard ground is available in most, but not all scenarios. Secondly, the study lacked secondary factors, such as stress of the rescuer. And lastly, real-life patients provide slightly different compression properties compared to mannequins. In addition to correct compression depth and rate, complete chest recoil after each compression is important. A drawback of all current accelerometer-based approaches is that insufficient chest recoil cannot be measured. Conclusion. We performed a data collection study with 20 participants. More than 5,000 chest compressions were recorded, covering a broad range of depth and rate. We contribute a comparison of 6 estimation algorithms and 3 wearable positions. Chest and ear wearables were evaluated for the first time. Most importantly, we found effective life-saving CPR support to be possible based on all wearable positions. Precise estimates of compression depth and rate were obtained at the wrist, chest and ear positions. Results regarding the popular Wearable platform are particularly encouraging given their broad availability and high user acceptance. Future work includes gyroscope integration and chest recoil detection. Thank you very much for your attention.